plot here. So the way it would do is each of the respective branch would go in this way. For example, one of the branches go in this way. The other branch would move in the opposite direction. Right? So for example, if this is V out 1, because we know it started from VDD and slowly it went down, and this is V out 2, where it starts off with 0 and slowly turns out to be 1. So when you have these two areas, what is this voltage value? What is this voltage value? What is the maximum voltage value? The voltage values that you would see here are VDD and this is right? These are the two things. Now in this waveform, what do you additionally observe? Our observation, or what I would like to draw your attention to, is what is the maximum slope and minimum gain. So what is the gain and slope information? Gain and slope information. So what do you mean when the delta V? Slope is typically going to show you for your delta output, what is the delta input that is needed. That will give you a slope, and this is also defined as your gain, or that instantaneous gain. Now if I draw your attention to these flat regions, right? These flat regions are minimum slope and minimum gain. So these are going to be your flat regions because there is no slope, not much of a slope here. So what would happen on the other side where there is maximum slope? This region is filled with maximum slope. So where you have max slope, right? You have max slope and max gain. So here, what do you identify here? Let me remind you here, single stage amplifier. Single stage amplifier, what was it? We had the same for a common source amplifier, right? Where you had three areas. Flat areas, and this is your area. So this was your saturation, right? One was cut off, another was triode. So what did this become? Yellow areas became digital functions, only 1 and 0. Purple became analog functions. Similarly, you will have this area here. All the yellow region, you will have your static area or non-linear area, and purple will be your linear areas. So this is again going to be digital circuits. Okay, or your digital logic can be used. 1 and 0, 0 and 1. Right? This can be your 1 and 0 signal. And this area is going to be your analog area, linear. This is non-linear. So this area you will have amplification, right? This is going to be the amplifier area. Here, no amplification. Okay. but they will rail to rail in the opposite direction. Here you will either get strong values, either it is going to be closer to VDD or closer to ground. But if you observe here, the 0 that I am defining here is still closer to VDD. It is dependent on what is ISS over RD. So now you can define depending upon what is the value that you would prepare and get it output. And for that, this line is going to be beneficial in the analysis. So what do? The maximum and minimum levels are independent of the common mode input, right? Max is VDD, min is VDD minus ISS RD. So there is no dependence on the common mode value. You are only dependent on the ISS current and RD that is present. So there is no dependence on VL. Second is the circuit becomes more nonlinear as V1 minus V2 increases. So as the difference between these two increases, the output increases. So you enter the nonlinear region when V1 minus V2 is very large, or V2 minus V1 is very large. Okay, you enter into the nonlinear region. And when you are around the V1 equal to V2 region, okay, it is exactly said to be in equilibrium. Okay, or you are in the linear range. So if you want to operate a differential pair in the amplification region, keep their values as close to the respective Vins. So Vin plus minus Vin2, if you keep them close, you will see a very high ratio. If the difference between the two is very large, then you will see the circuits entering non-linear region. Okay, so this is called a qualitative analysis. Okay, qualitative analysis for a differential input. This is for single stage. This is for differential input.